What if the universe's greatest secret isn't hidden in the vastness of space or the depths of black holes, but in something as small as a single molecule? The ingredients for life itself, the very building blocks that sparked existence, might have been floating in the cosmos long before Earth even existed. Imagine that for a moment, the same organic molecules that make up your body, your thoughts, even your dreams, could have traveled across galaxies, riding comets or swirling in ancient stardust. How did these tiny fragments of chemistry come to be? And what do they tell us about our place in the universe? For decades, scientists have been piecing together clues from meteorites, distant nebulae, and even the harsh conditions of deep space, searching for answers to one of humanity's oldest questions: where did life begin? The theories are as wild as they are fascinating. Some suggest lightning strikes on a primordial Earth. Others point to icy comets delivering life's blueprints like cosmic postmen. Then there are the ideas that stretch the imagination even further. Could ultraviolet light from newborn stars have sparked the first organic molecules? Or did they form in the crushing depths of interstellar clouds where temperatures hover just above absolute zero? Today, we're diving into 30 of the most compelling theories about how the universe's first organic molecules came to exist. From the bizarre to the brilliant, these ideas aren't just about chemistry, they're about unraveling the story of us. Because every atom in your body, every strand of DNA has a history written in the stars. So let's journey back to the very beginning, to a time before planets, before life, even before the first spark of creation. Because somewhere in these theories lies the answer to how we got here, and maybe, just maybe, where we're headed next. One of the most enduring theories about life's origins takes us back to Earth's earliest days, when our planet was a swirling, chaotic place of volcanoes, violent storms, and vast, shallow oceans. Picture a world where the air was thick with methane and ammonia, where lightning split the sky and ultraviolet radiation beat down unimpeded, no ozone layer to soften the blow. In this primordial soup, scientists believe the first organic molecules might have been born. The idea took center stage in 1953 when Stanley Miller and Miller-Urey conducted a now famous experiment. They filled a glass apparatus with water, methane, ammonia, and hydrogen gases thought to mimic Earth's early atmosphere, then zapped the mixture with electrical sparks to simulate lightning. Within days, the once clear liquid turned pink, then a murky brown. When they analyzed it, they found amino acids, the very building blocks of proteins and life itself. It was a revelation. The chemistry of life, they argued, could emerge from simple ingredients and a little energy. But science never stands still. Over time, critics pointed out flaws in the primordial soup hypothesis. Earth's early atmosphere, newer research suggests, might not have been as rich in methane and ammonia as Miller and Urey assumed. Instead, it may have been dominated by carbon dioxide and nitrogen, gases far less reactive in forming organic molecules. And yet, even with these doubts, the experiment's legacy endures. Modern variations, using updated atmospheric models and different energy sources, still produce amino acids under conditions closer to what early Earth might have actually been like. So was the primordial soup the only kitchen where life's ingredients were cooked up? Probably not. But it showed us something profound, that under the right conditions, the leap from chemistry to biology might not be as impossible as it seems. And if that's true for Earth, could it also be true for countless other worlds, simmering in their own versions of that ancient life-brewing broth? Deep beneath the ocean's surface, where sunlight never reaches and the pressure could crush a submarine, lies another potential cradle for life's first molecules. Hydrothermal vents, towering chimneys of mineral-rich water spewing from Earth's crust, create an otherworldly landscape of extremes. Temperatures soar to hundreds of degrees near the vents, then plunge to near freezing just steps away. The water is packed with hydrogen sulfide, metals like iron and nickel, and a cocktail of chemicals that would be toxic to most life today. Yet in this hostile environment, scientists are finding clues that these vents might have been perfect laboratories for cooking up organic molecules billions of years ago. The theory goes like this: as superheated water surges through cracks in the ocean floor, it dissolves minerals from the surrounding rock. When that scalding fluid meets the icy seawater, it creates a turbulent mixing zone where chemistry goes into overdrive. The minerals act like catalysts, helping simple molecules like carbon dioxide and hydrogen link up into more complex structures. In recent years, researchers have discovered amino acids, the same ones Miller and Urey made with lightning, forming near these vents under conditions that mimic Earth's ancient oceans. But what makes this idea even more compelling is how it solves one of the primordial soup theory's biggest puzzles: stability. On the early Earth's surface, ultraviolet radiation and asteroid impacts would have constantly scrambled delicate organic molecules. Down by the vents, though, the ocean acted as a protective shield, while the vents themselves provided a steady supply of energy and raw materials. It's like comparing a fragile sandcastle on a stormy beach to a reinforced lab buried deep underground. One offers shelter and endless fuel for chemical experiments. And the discoveries keep coming. In 2017, scientists studying the Lost City hydrothermal field, a network of vents in the Atlantic, found organic molecules forming without any help from living organisms. Even more astonishing, some of these molecules were assembling into tiny cell-like structures, hinting at how life might have taken its first tentative steps toward complexity. Could this be where it all began? The vents certainly check many boxes: energy, protection, and a never-ending flow of ingredients, but the story doesn't end there. Because if life's building blocks can form in the crushing dark of Earth's oceans, what's stopping the same process from happening on icy moons like Europa or Enceladus, where hydrothermal vents might still be active today? The universe, it seems, has a way of turning even the most inhospitable places into crucibles for creation. Now let's consider something even more mind-bending. What if life's ingredients didn't start on Earth at all? Imagine organic molecules as cosmic hitchhikers, catching rides on comets or meteorites and raining down on our planet like a delivery from the stars. This is the bold idea behind Panspermia, the theory that the building blocks of life, or even life itself, could have traveled across space before taking root here. One of the most compelling pieces of evidence for this theory comes from a meteorite that crashed near Murchison, Australia in 1969. When scientists analyzed its contents, they found over 70 different amino acids, some of the same ones found in proteins essential for life on Earth. But here's the kicker: many of these molecules were in forms that don't naturally occur in terrestrial biology. They had to have formed somewhere else, likely in the cold, dark reaches of interstellar space or on ancient asteroids. Critics, of course, have pushed back. Could contamination from Earth explain the findings? Rigorous testing has ruled that out. The amino acids inside the Murchison meteorite were trapped in its structure long before it ever hit our atmosphere. Others argue that even if organic molecules arrived from space, that doesn't necessarily mean they sparked life. Space's brutal radiation, extreme temperatures, and the violent journey through Earth's atmosphere would have battered fragile molecules. Yet experiments show some organic compounds shielded inside asteroids or comets could survive the trip. But Panspermia doesn't just raise questions about how life began, it reshapes our view of where it might exist. If organic molecules are hardy enough to traverse the cosmos, could they have seeded life on other worlds too? Some researchers speculate that Mars, with its once flowing water, might have been a way station for life's ingredients before they reached Earth. Others go even further, suggesting entire microbial life forms could have made the journey, tucked safely inside protective rock. The universe, it seems, might be far more interconnected than we ever imagined. Whether panspermia is the full story or just one chapter in life's origins, it forces us to look beyond our planet, because the answer to how we got here might still be floating out there, waiting to be discovered. Out in the cold, dark void between stars where temperatures drop to just a few degrees above absolute zero, something remarkable is happening. These so-called empty spaces are actually filled with vast clouds of dust and gas drifting for millions of years. And within these interstellar nurseries, scientists are discovering that complex organic molecules might be forming right under our noses, or rather above them. Take glycolaldehyde, for instance. This simple sugar molecule, a cousin to the table sugar in your kitchen, was spotted by the ALMA telescope in regions where new stars are being born. How does something as delicate as sugar survive, let alone form, in the harsh environment of space? The answer lies in the icy grains floating in these clouds. Picture tiny specks of dust, each coated in a frozen shell of water, methane, and carbon monoxide. When cosmic rays, high-energy particles racing through the galaxy, smash into these grains, they trigger chemical reactions that shouldn't be possible in such extreme cold. Here's the wild part. These reactions don't just create simple molecules. Laboratory experiments simulating space conditions have shown that under the right circumstances, these ices can build complex organics like amino acids and even the precursors to RNA. It's as if the universe has a hidden chemistry lab, quietly assembling life's ingredients in the darkest corners of the cosmos. But why does this matter? Because these dust clouds aren't just passive factories, they're also delivery systems. When new stars and planets form, they pull material from these clouds, carrying those pre-made organic molecules along for the ride. Some researchers speculate that Earth might have been seeded with these space-borne compounds early in its history, giving life a head start, and the discoveries keep piling up. ALMA has since spotted other organics like methanol and formaldehyde in similar regions. Each finding suggests that the universe is far more chemically creative than we ever imagined, capable of building the very blocks of life long before planets like ours even existed. So next time you gaze up at the night sky, remember, those dark patches between the stars might not be empty at all. They could be simmering with the ingredients that eventually made you. Picture this, a beach on early Earth, but not the kind you'd recognize today. Instead of golden sand, these shores glittered with something far more extraordinary: grains of radioactive minerals like uranium and thorium washed up by ancient tides. And it's here, in this unlikely setting, that scientists believe another recipe for life's first molecules may have been brewing. The radioactive beach hypothesis suggests that the energy needed to forge organic compounds didn't just come from lightning or hydrothermal vents. It might have been supplied by the steady decay of these radioactive sands. Imagine each grain as a tiny power plant, emitting particles and gamma rays over millennia. When these emissions interacted with the surrounding water and gases like carbon dioxide and nitrogen, they could have sparked chemical reactions similar to those in the Miller-Urey experiment, but with a slow, persistent energy source instead of sudden jolts of electricity. What makes this theory stand out? A clue comes from zircon crystals, some of the oldest minerals on Earth, dating back over 4 billion years. Trapped inside these time capsules, researchers have found carbon signatures that hint at organic activity. Even more intriguing, some zircons formed in environments rich in radioactive elements, suggesting that these energy-packed settings could have been hotbeds for prebiotic chemistry. It's as if the crystals are whispering, life didn't need a dramatic catalyst, just patience and the quiet hum of atomic decay. But here's where it gets even more fascinating. Unlike lightning strikes or hydrothermal vents, radioactive beaches would have offered something unique: stability. While a storm might last hours and a vent's activity could fluctuate, radioactive decay ticks away like a clock, providing a consistent energy supply for thousands of years. Combine that with the ebb and flow of tides bringing fresh ingredients and washing away waste, and you've got a potential ideal factory for life's building blocks. Of course, it's not a perfect theory. Critics point out that radiation can also break apart complex molecules, not just create them. Yet lab experiments show that under the right conditions, like those in wet, mineral-rich sands, the balance tips toward synthesis rather than destruction. It's a delicate dance, but one that the early Earth, with its patchwork of environments, might have mastered in ways we're only beginning to understand. So next time you walk along a beach, consider this. The shorelines we find peaceful today could have once been cosmic kitchens where the faint glow of radioactivity quietly assembled the pieces of what would one day become you. And if that's true, it raises another tantalizing question. How many other worlds with their own radioactive shores might be stirring the same primordial soup right now? Volcanoes have long been seen as forces of pure destruction, rivers of molten rock, choking ash clouds, landscapes reshaped in an instant. But what if these titanic eruptions were also secret chemists, forging the ingredients of life even as they tore the Earth apart? That's the startling idea behind volcanic lightning, a phenomenon where the very chaos of an eruption generates electrical storms powerful enough to rewrite chemistry. Here's how it works. When a volcano erupts, it blasts countless particles of ash and rock into the sky at speeds approaching the sound barrier. These colliding fragments strip electrons from one another, building up massive static charges like rubbing a balloon on your hair, but scaled up to apocalyptic proportions. The result: lightning bolts hotter than the surface of the sun, crackling through the ash plume in a display of raw energy. And it's in these blinding flashes that something extraordinary happens. Laboratory experiments simulating volcanic lightning have shown that these discharges can transform simple gases like the carbon dioxide and nitrogen spewing from eruptions into amino acids such as aspartic acid, a key component of proteins. Researchers recreated these conditions by firing high-voltage sparks through mixtures resembling volcanic plumes, and the results were undeniable. The same molecules life uses to build itself were forming in minutes. But why does this matter beyond just another way to make organic molecules? Unlike Miller and Urey's primordial soup or hydrothermal vents, volcanic lightning offers something unique: scale. A single eruption can generate thousands of lightning strikes over hours or days, each one a potential factory for life's building blocks. And since volcanic activity was far more common on the early Earth, these storms could have been raining organic molecules onto the planet's surface continuously, seeding countless environments at once. The implications stretch beyond our planet too. Mars, with its massive ancient volcanoes like Olympus Mons, might have experienced similar electrical storms in its wetter past. Even icy moons like Io, Jupiter's hypervolcanic satellite, could be churning out organic molecules in their ash plumes right now. It's a reminder that life's ingredients might not need gentle, stable environments sometimes. The most violent corners of the universe could be cooking them up in the chaos. So next time you see footage of a volcano's fury, look closer. Those jagged bolts of lightning aren't just spectacle, they might be echoes of the very sparks that helped set the stage for life itself. Among the countless molecules drifting through space, one unassuming compound might hold a key to life's origins: formamide. This simple liquid, made of just hydrogen, carbon, nitrogen, and oxygen, is far more than a laboratory curiosity. It's been spotted in comets, interstellar clouds, and even the atmospheres of distant planets. And here's the astonishing part. Under the right conditions, formamide can transform into the very letters of life's genetic alphabet. The process begins when formamide encounters energy, whether from the searing ultraviolet light of young stars or the geothermal heat bubbling up from Earth's crust. In lab experiments, scientists have recreated these conditions, exposing formamide to intense UV radiation or heating it to temperatures found near volcanic vents. What emerges isn't just random chemistry. Over time, the molecules link up into nucleobases adenine, guanine, cytosine, and uracil, the same molecules that form the rungs of DNA and RNA's twisted ladders. It's as if the universe encoded a recipe for life's blueprints into this humble substance. But why does this pathway stand out? Unlike other theories that require precise mixes of gases or rare minerals, formamide is a one-stop shop. It contains all the necessary atoms in a single package, and the energy needed to trigger its transformation is abundant in both space and Earth's early environments. Studies in 2016 showed that when formamide interacts with common meteoritic minerals like olivine or zircon, the reaction speeds up dramatically, churning out nucleobases at rates that could have filled primordial pools in geologic timeframes. The implications are staggering. If formamide was delivered to Earth by comets or asteroids, or even formed here through atmospheric chemistry, it could have provided a ready-made stockpile of life's raw materials. And it's not just about our planet. Recent telescope observations have detected formamide in the protoplanetary disks around young stars, suggesting that any emerging worlds there might be receiving the same molecular starter kit. Critics caution that while the lab results are compelling, nature's version of this process would have been messier with competing reactions and unpredictable environments. Yet, even if only a fraction of formamide successfully polymerized, that might have been enough. After all, life doesn't need perfection, just a foothold. And if a molecule as common as formamide can bridge the gap between chemistry and biology, then the universe might be far more generous with life's ingredients than we ever dared hope. Asteroid impacts are often framed as extinction-level events, cataclysmic forces that erase life rather than create it. But buried in the aftermath of these violent collisions lies a paradox. The same unimaginable heat and pressure that can sterilize a landscape might also be the perfect crucible for forging life's essential molecules. Picture a space rock the size of a mountain screaming through the atmosphere at 20 kilometers per second, slamming into Earth with enough energy to vaporize rock. In the chaos that follows as the crater cools and the steam condenses, something unexpected stirs in the chemical wreckage, organic compounds born from the very violence that seemed to forbid them. The Sudbury Basin in Canada tells this story better than anywhere else. Formed nearly 2 billion years ago by an impact so massive it melted part of Earth's crust, this crater, now a sprawling geological formation, is laced with hydrocarbons, the molecular skeletons of more complex organics. Researchers analyzing Sudbury's rocks have found chains of carbon atoms resembling the building blocks of fats and oils, substances crucial for cell membranes. How did they get there? The leading theory suggests that the impact shock waves reaching pressures hundreds of thousands of times greater than Earth's surface forced carbon dioxide and water to rearrange into new forms, while superheated metals in the impact melt acted as catalysts. It's as if the collision momentarily turned the crater into a high-pressure chemistry set, where raw elements were hammered into life's precursors. Lab experiments back this up. Using high-powered guns to simulate asteroid strikes, scientists have blasted metal projectiles into mixtures resembling early Earth's crust and atmosphere. The results: amino acids and nucleotide bases emerging from the chaos, proving that impacts could indeed be factories, not just destroyers. What's even more compelling is the timeline. During Earth's first billion years, asteroids bombarded the planet relentlessly, meaning these violent synthesis events wouldn't have been rare anomalies, but regular occurrences, constantly churning out fresh batches of organic material. But here's where the theory twists into something even grander. If impacts could forge organics here, why not elsewhere? Mars, with its own history of cataclysmic strikes, shows signs of ancient hydrothermal activity in its craters, a potential setup for post-impact chemistry. Even Saturn's moon Titan, where hydrocarbon lakes already dot the surface, might have experienced impact-driven reactions that pushed its chemistry toward greater complexity. The lesson is counterintuitive but profound. Sometimes creation requires destruction first. So the next time you see a shooting star, remember, those fleeting flashes aren't just debris burning up. They're echoes of a time when the universe built as fiercely as it destroyed, and in the fiery aftermath of collisions, the ingredients for life might have found their start. Out in the deepest voids of space, where temperatures plunge to -260°C, an unexpected alchemy is at work. Far from being empty, these frigid molecular clouds, vast regions of dust and gas spanning light years, are cosmic kitchens quietly assembling some of life's most essential ingredients. Here, in the bitter cold where even molecules should freeze solid, methanol and formaldehyde form in abundance, floating among the ice-coated dust grains like microscopic snowflakes waiting for their moment. The Herschel Space Observatory opened our eyes to this paradox. Peering into clouds like Sagittarius B2, a massive star-forming region near our galaxy's center, Herschel detected staggering amounts of these simple organic molecules, enough to fill billions of comets. What makes this discovery extraordinary is the environment. At these temperatures, most chemical reactions grind to a halt, but on the surface of dust grains, something defies expectations. Atoms and molecules, slowed by the cold, actually have more time to stick together when they collide. Hydrogen atoms skitter across icy surfaces, bonding with carbon monoxide to form formaldehyde, which then reacts further to create methanol. It's a slow-motion dance choreographed by quantum physics. But these clouds aren't just passive storage lockers. When nearby stars ignite, their radiation warms pockets of these clouds, allowing trapped molecules to sublimate into gas. Some get incorporated into newborn planetary systems, while others hitch rides on comets, like the Rosetta mission's discovery of formaldehyde and methanol on Comet 67P. Suddenly, the fragile organics forged in deep cold find themselves cast into warmer environments where they can participate in new chemistry. The implications rewrite our understanding of life's origins. Instead of needing perfect conditions on a young planet, many of life's starter molecules might have been prefabricated in these interstellar freezers, preserved for millions of years until stellar nurseries or planetary impacts gave them a second act. It's as if the universe perfected a cosmic deep freeze method, prepping ingredients in advance so they'd be ready the moment warmer kitchens became available. And the discoveries keep coming. Recent radio telescope observations reveal even more complexity in these clouds, with molecules like ethylene glycol, a cousin to antifreeze, hinting that the cold might be capable of crafting far more than we ever imagined. So while these regions may seem lifeless at first glance, they could be the universe's quietest, most patient chemists, assembling the very pieces that would one day stir awake as biology. This changes how we search for life beyond Earth. If complex organics form readily in the darkest corners of space, then planets orbiting even young stars might inherit a head start. The building blocks may already be waiting, frozen in time until the right conditions thaw them into action. It's a humbling reminder, sometimes life's most critical steps don't happen in warmth and light, but in the silent, icy dark between the stars. High above Earth's surface, where the air thins and sunlight strikes unfiltered, another unexpected player might have contributed to life's molecular origins: photochemical hazes. These aren't ordinary clouds, they're dense, organic, rich blankets of tiny particles, similar to the orange smog enveloping Saturn's moon Titan. While we often think of hazes as obstacles for astronomers or annoyances for photographers, they could have served as cosmic chemistry labs in Earth's early skies. The process starts with simple gases like methane and nitrogen, bathed in ultraviolet light from the young sun. As photons smash into these molecules, they tear them apart, creating reactive fragments that swiftly recombine into more complex structures. But here's the twist: instead of dispersing, these new compounds clump together into aerosol particles, suspended in the atmosphere like microscopic floating reactors. Shielded from destructive radiation by the haze itself, these particles provide a safe haven where chemistry can play out over weeks or months, far longer than free-floating molecules would survive. Laboratory simulations reveal just how creative this process can be. When scientists recreate early Earth's atmosphere in chambers and expose it to UV light, the resulting hazes contain amino acids and nucleotide bases, the raw materials of proteins and DNA. Even more astonishing, some experiments produce molecules like adenine, a key component of ATP, the energy currency of all living cells. It's as if the haze acts like a sieve, filtering out the noise of random reactions and selectively amplifying the ones that matter most for biology. What makes this theory especially compelling is its universality. Titan's haze, studied by the Cassini mission, shows eerily similar chemistry despite its frigid alien environment. Tholin's complex organic polymers forged in its atmosphere rain down onto the Moon's surface, painting its dunes orange and filling its methane lakes with organic sludge. If this happens on Titan, why not on a younger, warmer Earth? The parallels suggest that photochemical hazes might be a common feature of planets with the right atmospheric ingredients, turning entire skies into assembly lines for life's building blocks. Yet the haze hypothesis isn't without hurdles. Critics point out that while these reactions produce organic molecules, they also generate toxic byproducts like cyanide, hardly ideal for budding life. But here's where the theory gets clever. Recent studies show that when these hazes settle into water, cyanide can actually fuel further chemistry, helping form even more complex molecules like sugars and peptides. It's a reminder that what seems poisonous in isolation might be transformative in the right context. So picture Earth's skies 4 billion years ago, not clear and blue, but stained amber with organic smog. Every sunrise drives trillions of chemical reactions in the air itself, while microscopic particles drift downward like snow, carrying their precious cargo of prebiotic molecules into waiting oceans. Far from being a barrier to life, this haze might have been its architect, a slow, steady drizzle of possibility from the heavens above. Picture a world where the first stages of life didn't unfold in water or air, but in the quiet, unassuming surfaces of mud. This is the heart of the clay mineral catalysis theory, which suggests that ordinary clay might have been the universe's first molecular workshop. At first glance, clay seems inert, just layered silicates formed by weathered rock. But zoom in closer, and you'll discover a microscopic landscape of ridges, valleys, and charged surfaces perfect for trapping and organizing the building blocks of life. The magic lies in clay's structure. Each flake is made up of stacked layers like pages in a book, with just enough space between them to cradle organic molecules. These surfaces carry subtle electrical charges that attract and hold onto amino acids, sugars, and other precursors, concentrating them far beyond what a random soup of chemicals could achieve. In the 1980s, chemist James Ferris demonstrated this brilliantly by showing how clays like montmorillonite could not only gather these molecules but also act as scaffolds, helping them link into chains forming peptides, the shorter cousins of proteins. The clay wasn't just a passive observer, it was an active participant guiding chemistry toward complexity. But why does this matter? Because life isn't just about having the right ingredients, it's about organizing them. In a vast ocean or a chaotic atmosphere, molecules might bump into each other randomly, but the odds of forming something as intricate as a protein are astronomically low. Clay changes that equation. Its surfaces act like a molecular conveyor belt, bringing the right pieces together in the right orientations, shielding them from degradation, and even providing the energy, through subtle shifts in its layers, to drive reactions forward. It's as if Earth's geology handed life a cheat code, simplifying the leap from disorder to order. Recent experiments have added even more depth to this idea. When researchers simulate early Earth conditions with clay-rich environments, they've observed not just peptide formation, but also the assembly of cell-like structures, tiny compartments that could have been precursors to actual cells. Some clays even catalyze the creation of RNA-like molecules, hinting that these humble minerals might have played a role in both genetics and metabolism. Critics argue that while clays are useful, they aren't the only game in town. Hydrothermal vents and atmospheric hazes could have achieved similar feats. But here's what sets clay apart: durability. Unlike fleeting lightning strikes or temporary vents, clay beds could persist for millions of years, offering a stable stage for chemistry to play out across generations. And the evidence isn't just in labs. Ancient sedimentary rocks, some of the oldest on Earth, show traces of clay-rich environments that coincide with the timeline for life's emergence. So next time you see a patch of wet clay, consider this. Beneath its unremarkable surface might lie echoes of a process that turned simple chemistry into biology. And if that's true, then the search for life elsewhere shouldn't just focus on water or energy, but on the quiet, unassuming minerals that could have been the universe's first architects of complexity. Imagine a world where life didn't start with DNA or proteins, but with something far simpler: a chemical reaction on the surface of a fool's gold. This is the radical idea behind Gunther Wechtersheuser's Iron-Sulfur World theory, which flips the traditional script on life's origins. Instead of genes first, metabolism first. Instead of gentle chemistry, a fiery dance of electrons on the jagged faces of pyrite, the mineral we often call fool's gold for its deceptive glitter. At the heart of this theory lies a simple but profound observation: metabolism. The cascade of reactions that power every living cell might have predated genetics altogether. Wechtersheuser, a chemist turned patent lawyer with a knack for disruptive ideas, proposed that the first living systems weren't cells or molecules, but chemical cycles clinging to the surfaces of iron-sulfur minerals near hydrothermal vents. These minerals, particularly pyrite, have a unique property. When they form, they release tiny bursts of energy. That energy, Wechtersheuser argued, could have fueled the assembly of organic molecules, kickstarting a primitive version of metabolism before anything resembling a cell existed. The beauty of this idea lies in its elegance. Pyrite forms naturally when hydrogen sulfide from vents reacts with iron in seawater, creating a charged surface that acts like a molecular conveyor belt. In lab experiments simulating these conditions, researchers have watched as simple molecules like carbon monoxide latch onto pyrite, then get coaxed into more complex structures like acetic acid, a key player in modern metabolism. It's as if the mineral's surface serves as both catalyst and power source, a kind of prehistoric battery driving chemistry toward complexity. Critics, of course, have raised eyebrows. Without genetic material to guide and replicate these reactions, could this truly be called life? Wechtersheuser's response is provocative. Maybe life didn't need genes at first. Maybe it began as a self-sustaining chemical whirlwind, with minerals like pyrite acting as scaffolds, holding the reactions in place until genetic molecules like RNA could emerge and take over. The vents would have provided a steady stream of raw materials, while the pyrite's energy kept the whole system humming, and the evidence isn't just in labs. Modern microbes still use iron-sulfur clusters at the core of their metabolic machinery, a possible relic of this ancient mineral-driven past. Even more tantalizing, NASA studies of alkaline hydrothermal vents, where pH gradients mimic batteries, show how similar reactions could generate energy without sunlight or oxygen. It's a reminder that life might not have needed a gentle start, just a rocky surface, a spark of chemistry, and time to build something extraordinary. So next time you see pyrite glinting in a rock, remember, this so-called fool's gold might have been the universe's first power plant, quietly jump-starting the reactions that would one day become you. And if that's true, it changes not just how we see life's origins, but how we might recognize it elsewhere. On worlds without water or DNA, perhaps all life needs is the right kind of rock and a little chemical persuasion. Deep in the icy reaches of space, where temperatures barely whisper above absolute zero, another surprising molecular factory might be at work, powered not by heat or lightning, but by the silent rain of cosmic rays. These aren't ordinary particles, they're fragments of atoms accelerated to nearly the speed of light, hurled across the galaxy by supernova and black holes. When they slam into the frozen surfaces of interstellar dust grains or comets, something remarkable happens. Simple molecules get stitched together like threads in a cosmic tapestry, forming the long chains that life relies on. This process, called cosmic ray polymerization, turns the barren cold of space into an unlikely workshop. Picture a grain of dust coated in a frosty shell of water, methane, and ammonia, molecules so basic they seem inert. But when a cosmic ray pierces this icy layer, it doesn't just pass through harmlessly. The collision unleashes a storm of secondary particles and radiation, blasting the ice with enough energy to break molecular bonds and forge new ones. In lab experiments that mimic these conditions, scientists have watched as mixtures resembling interstellar ice transform into complex organics like ethanol and even amino acids, all under the simulated bombardment of cosmic rays. What makes this pathway so intriguing is its sheer ubiquity. Cosmic rays permeate the galaxy, meaning no corner of space is truly free of their influence. While other theories require specific environments, volcanic beaches, hydrothermal vents, or atmospheric hazes, this one suggests that the building blocks of life could have been assembling everywhere, from the edges of molecular clouds to the frozen outskirts of young solar systems. And because the reactions happen in ice, the resulting molecules remain trapped and protected, preserved for millions of years until a passing star's warmth or a planetary collision sets them free. Recent studies add even more weight to the idea. When researchers analyzed organic material extracted from meteorites like Murchison, they found molecules with branching structures and unusual isotopes, telltale signs of cosmic ray chemistry. Even more compelling, the Rosetta mission's discovery of the amino acid glycine on Comet 67P aligns perfectly with models of cosmic ray-driven synthesis in icy bodies. It's as if the universe has been quietly knitting life's ingredients together in the dark, one high-energy particle at a time. Yet the theory isn't without its puzzles. Cosmic rays can also destroy complex molecules just as easily as they create them, leading to a delicate balance between construction and demolition. Some researchers argue that for polymerization to win out, the ice layers need just the right thickness enough to shield nascent molecules from total destruction, but not so much that the cosmic rays lose all their energy before reaching the reactive zone. It's a Goldilocks scenario where the conditions have to be just right, but here's the thrilling implication. If cosmic rays can build complexity in the void, then the raw materials for life might be far more widespread than we ever imagined. Planets forming around distant stars could inherit these pre-made organics, baked into their very foundations. Even moons like Europa, with its subsurface ocean and icy shell, might harbor molecules forged by this relentless particle rain. The universe, it seems, doesn't need gentle nurseries to cook up life's ingredients sometimes. All it takes is a barrage of atomic shrapnel and a patience spanning eons. Along coastlines where the tides roll in and out with ancient rhythm, another subtle but powerful force might have shaped life's earliest chemistry, the rise and fall of water in shallow pools. Picture a rocky shoreline on early Earth where puddles left behind by the retreating tide bake under the sun, shrinking by the hour. As the water evaporates, something remarkable happens. The once dilute organic molecules floating within become tightly packed, forced into close quarters. In this confined space, reactions that would take years in open water can unfold in days or even hours. This is the essence of tidal pool cycling, where the simple act of drying and rewetting could have turbocharged the journey from chemistry to biology. What makes this theory compelling is its sheer simplicity. Unlike elaborate hydrothermal vents or violent asteroid impacts, tidal pools require no extreme conditions, just the natural ebb and flow of water under sunlight. Experiments show that when amino acids or nucleotides are subjected to repeated wet-dry cycles, they don't just survive the dehydration, they thrive. The drying phase drives molecules together, encouraging bonds to form. Then, when the tide returns or rain refills the pool, fresh water dissolves these new compounds, allowing them to interact in ways they couldn't before. It's like nature's version of a stirring rod, mixing ingredients over and over until complexity emerges. One striking example comes from studies of RNA, the molecule many scientists believe predated DNA in early life. In the lab, researchers have recreated tidal pool conditions, alternating between wet and dry phases while observing RNA strands. Remarkably, these strands not only grow longer but also begin to self-replicate, copying themselves without any help from enzymes or modern cellular machinery. The cycles essentially act as a training ground, teaching molecules to cooperate and persist in a changing environment. But tidal pools offer more than just concentration. Their mineral-rich edges, often lined with clays or volcanic rock, provide surfaces that stabilize fragile molecules. Some minerals even act as catalysts, lowering the energy needed for key reactions. And the timing is perfect. With early Earth's faster rotation, tides would have risen and fallen more frequently than today, creating endless opportunities for this chemistry to play out. Of course, skeptics point out that ultraviolet radiation on the surface could have broken down delicate organics faster than they could assemble. Yet recent fieldwork in modern analogues, like Australia's Shark Bay, where microbial mats thrive in sun-baked tidal flats, suggests that even under harsh light, protective layers of sediment or mineral coatings could have shielded early reactions. The beauty of this idea lies in its universality. Shorelines exist on any world with liquid water and gravity, meaning tidal pools could have been at work on Mars when it had seas, or might still be active today on Saturn's moon Titan, where methane ebbs and flows against icy banks. Life, it seems, might not need elaborate factories to begin, just the patient repetition of waves and sunlight, turning shallow puddles into cradles of complexity. So next time you stand at the edge of the ocean, watching a tide pool glisten under the sun, consider this. Those unassuming pockets of water may hold the secret to how chemistry first crossed the threshold into biology. And if that's true, then the rise of life might not have been a stroke of cosmic luck, just the inevitable result of time, tides, and the tireless rhythm of evaporation. Hydrogen cyanide might sound like the last place you'd look for life's origins after all. It's a deadly poison in concentrated doses. But this simple molecule, just one atom each of hydrogen, carbon, and nitrogen, could hold the key to how the universe built the very first genetic blueprints. Floating in comets, drifting through interstellar clouds, or simmering in Earth's early atmosphere, HCN has a hidden talent. Under the right conditions, it can stitch itself into the nucleobases that form DNA and RNA. The magic happens when ultraviolet light or other energy sources hit hydrogen cyanide molecules, driving them to link up into long chains called polymers. In the 1960s, chemist Juan Oro demonstrated this brilliantly by dissolving HCN in water and exposing it to mild heat, no fancy lab equipment required. Over days, the clear solution turned dark, and when he analyzed the contents, there it was, adenine, one of the 4 key letters in life's genetic alphabet. This wasn't just a fluke. Later experiments showed that under conditions mimicking space or early Earth, like freezing temperatures or UV radiation, HCN polymers could produce not just adenine, but guanine and even amino acids too. What makes this pathway so compelling is its simplicity. Unlike theories requiring rare minerals or precise environments, hydrogen cyanide is everywhere in the cosmos. Comets like Hale-Bopp carry vast amounts of it. The haze of Saturn's moon Titan is laced with HCN. Even meteorites contain traces of its polymers and the energy needed to trigger these reactions. UV light from young stars or electrical storms would have flooded the early solar system, meaning the universe practically set the stage for this chemistry to run on autopilot. But here's the twist: HCN's versatility doesn't stop at nucleobases. Under slightly different conditions, like those near volcanic vents or tidal pools, the same polymers can break down into glycine, the simplest amino acid. It's as if hydrogen cyanide is a molecular multitool, capable of forging multiple pieces of life's puzzle depending on where it lands. Critics highlight the elephant in the room: cyanide's toxicity. Yet in dilute concentrations, especially when bound up in polymers, it's far less dangerous. Some researchers even argue that small amounts of HCN could have acted as a chemical catalyst, driving other reactions forward while gradually transforming into safer compounds. The implications are staggering. If adenine and other bases could form this easily, then life's genetic code might not be the product of rare chance, but an inevitable outcome of cosmic chemistry. And with hydrogen cyanide so abundant from comets to interstellar dust, the raw materials for biology could have been raining down on countless worlds. So next time you hear about cyanide, remember, this feared poison might have been the universe's way of writing life's first draft, one polymer at a time. Beneath Earth's turbulent surface, where crushing pressures and searing temperatures create a world of extremes, another hidden stage for life's origins might have been set. Far from the chaos of asteroid impacts or the fury of ultraviolet radiation, the deep crust, a realm of solid rock and sluggish chemical reactions, could have provided the perfect sanctuary for organic molecules to assemble in slow motion, shielded from the violence above. This theory hinges on a paradox. The same forces that make Earth's depths seem inhospitable might actually foster stability. At depths of several kilometers, where tectonic plates grind and magma simmers, water becomes something stranger than the liquid we know. Superheated under immense pressure, it takes on new properties, dissolving minerals and gases that would never mix at the surface. In these cryptic pockets, carbon dioxide and hydrogen, squeezed from rocks or rising from the mantle, could have engaged in a patient dance, catalyzed by the very minerals surrounding them. Experiments simulating these conditions show that over thousands of years, simple molecules like formic acid and methanol emerge, building blocks for more complex chemistry. One striking piece of evidence comes from South Africa's Mponeng gold mine, where scientists discovered a community of bacteria thriving 2.8 kilometers underground, cut off from sunlight for millions of years. These microbes survive by harvesting energy from radioactive decay in the surrounding rock, proving that life can find a way even in the planet's most isolated corners. If single-celled organisms can persist there today, why couldn't precursor molecules have formed under similar conditions 4 billion years ago? But here's where the deep crust theory gets even more intriguing. Unlike surface environments where storms or tides might wipe away delicate chemistry, underground reactions could have unfolded undisturbed for eons. The heat and pressure, far from being obstacles, might have acted like a slow cooker, lowering the energy needed for key reactions while preventing newly formed molecules from breaking apart. Certain minerals like olivine or magnetite could have served as catalysts, their crystalline structures guiding carbon atoms into chains with almost molecular precision. Recent discoveries add weight to this idea. Analysis of fluid inclusions, tiny bubbles trapped in ancient rocks, reveals traces of organic compounds like ethane and propane, suggesting that hydrocarbon synthesis was happening deep below Earth's surface long before life emerged. Even more compelling, laboratory studies show that under crust-like pressures, these reactions accelerate, hinting that the deep Earth wasn't just a passive storage locker but an active factory. Critics argue that without some connection to the surface, whether through volcanic vents or groundwater circulation, these molecules would have remained trapped, never contributing to life's origin. Yet here, too, nature provides an answer. Geological processes like subduction or hydrothermal activity could have periodically tapped into these hidden reservoirs, ferrying their chemical treasures upward to mix with surface environments. The implications stretch beyond our planet. Mars, with its ancient volcanoes and suspected subsurface water, might have harbored similar deep crust chemistry. Even icy moons like Europa, where tidal forces heat the interior, could conceal pressurized pockets ripe for organic synthesis. So while the deep crust lacks the drama of lightning strikes or comet impacts, its quiet, relentless chemistry might have been just as vital, a slow-burning fuse that eventually ignited life's spark. And if that's true, then the universe's recipe for life might not always need a kitchen on the surface. Sometimes the most important cooking happens where no light reaches, in the patient darkness beneath the world. Among the elements essential for life, phosphorus rarely gets the spotlight, overshadowed by carbon's versatility or oxygen's abundance. But without this unassuming element, life as we know it wouldn't exist. Phosphorus forms the backbone of DNA, fuels cells with ATP, and even helps build cell membranes. So how did Earth's early environments provide enough of it to kickstart biology? The answer might lie in places where heat, water, and minerals conspired to unlock phosphorus from its rocky prison, geothermal hotspots and hydrothermal vents. Phosphorus is notoriously finicky in nature. On Earth's surface, it tends to bind tightly with calcium or iron, forming insoluble minerals that life can't easily access. But deep underground, where temperatures soar and acidic fluids circulate, something extraordinary happens. Experiments mimicking these conditions show that when phosphate-rich rocks like apatite encounter the acidic, mineral-laden waters of hydrothermal systems, phosphorus dissolves into forms that organic molecules can use. In 2021, researchers simulating ancient geothermal pools found that phosphate concentrations could soar to levels 1,000 times higher than in ordinary seawater, creating a broth rich enough to supply the first genetic and metabolic molecules. What makes this scenario so compelling is how it bridges geology and biology. Modern hydrothermal vents host bacteria that thrive on phosphorus, extracting it directly from minerals through clever chemistry. If microbes can do it today, why couldn't similar processes have acted billions of years ago? Recent studies of Iceland's steaming hot springs reveal another clue. Phosphorus doesn't just dissolve in these environments, it actively links up with organic molecules, forming stable compounds like phosphosters. These are the same bonds that hold DNA's structure together, hinting that geothermal systems might have been nature's first biochemistry labs. Yet there's a twist to this story. Phosphorus isn't just a passive ingredient, it might have played an active role in guiding chemistry toward complexity. In lab experiments, phosphate ions act as molecular glue, helping strands of RNA fold into functional shapes or stabilizing delicate protocells. Some scientists even speculate that phosphorus-rich minerals could have served as scaffolds, organizing other building blocks into patterns that eventually became genetic code. The implications stretch far beyond Earth. Mars's ancient volcanoes and subsurface hot springs, now silent, might once have unlocked phosphorus in similar ways. Even icy moons like Enceladus, with its suspected hydrothermal activity, could be hiding reservoirs of dissolved phosphate beneath their frozen shells. This changes how we search for life's origins, not just as a quest for carbon or water, but as a hunt for the places where chemistry conspired to free phosphorus from stone. So while phosphorus might lack the glamour of other elements, its role was anything but minor. Without it, life's blueprints would remain unreadable, its energy circuits broken. And if geothermal systems were the key to unleashing this element's potential, then the story of life's origins isn't just about molecules, it's about the hidden alchemy of heat, rock, and time. Think about the last time you bit into a perfectly baked pizza, the crispy crust, the bubbling cheese, the way heat transforms simple ingredients into something greater. Now imagine that same alchemy, but on a planetary scale. Welcome to the Prebiotic Pizza Hypothesis, where scientists propose that volcanic heat acting on thin mineral layers could have acted like nature's first oven, slow-cooking organic molecules into the precursors of life. At first glance, the idea sounds whimsical, but the chemistry is anything but. Picture a volcanic region on early Earth, where geothermal activity heats porous rocks like pumice or basalt stones riddled with microscopic channels. Water rich in simple carbon compounds seeps into these tiny crevices, and as the surrounding heat rises, it bakes the mixture gently, much like a pizza stone crisping dough. The result isn't toppings and cheese, but something far more profound. Concentrated pockets of amino acids and sugars, all trapped and protected within the mineral matrix. Lab experiments back up this deliciously strange idea. Researchers recreated these conditions by sandwiching organic-laden fluids between thin mineral sheets, then heating them to temperatures found near volcanic zones. Within hours, the mixture yielded complex molecules, including peptides and even small RNA-like chains. The key, it turns out, isn't just the heat, it's the confinement. By forcing molecules into tight spaces, the mineral layers act like a molecular sieve, increasing the chances they'll collide and react in ways that would rarely happen in open water. But here's where the theory gets even tastier. Unlike hydrothermal vents or tidal pools, which require specific geographies, this pizza oven effect could have happened almost anywhere volcanic activity met water and organics, making it a potential universal recipe. Modern analogues exist today in Iceland's geothermal fields, where steam rises through layered rocks, or even on Mars, where ancient lava flows once interacted with groundwater. Critics argue that the hypothesis lacks direct evidence in the geological record. No one's found a fossilized prebiotic pizza yet the simplicity is hard to ignore. No lightning strikes, no cosmic rays, just heat, water, and stone working in harmony. And if life's ingredients could really bake into existence this easily, then the universe might be serving up the building blocks of biology wherever volcanoes and oceans meet. So next time you enjoy a slice, remember, the same physics that perfects your dinner might have once helped perfect the chemistry of life itself. And if that's true, then the story of life's origins isn't just written in the stars or the deep sea. It might be tucked into the layers of a 4-billion-year-old cosmic kitchen. Imagine a comet, a frozen time capsule streaking through the solar system, its surface pockmarked by eons of cosmic radiation. These wandering ice balls might seem like passive relics, but beneath their icy shells, something extraordinary is brewing. When high-energy cosmic rays slam into a comet's surface, they don't just leave scars, they trigger a cascade of chemistry that could have stocked the early Earth with life's essential ingredients. The Rosetta mission, which orbited Comet 67P for 2 years, gave us front-row seats to this process. As the spacecraft analyzed the comet's icy surface, it detected glycine, the simplest amino acid and a cornerstone of protein. But here's the twist: glycine wasn't just sitting there passively. It was embedded in a layer of irradiated ice, a telltale sign that cosmic rays had transformed simple molecules like water, ammonia, and carbon dioxide into something far more complex. Lab experiments confirm this. When scientists blast comet-like ice mixtures with radiation, amino acids form within days. It's as if the universe packed comets with frozen chemistry sets, ready to activate the moment they're exposed to deep space particle storms. What makes this theory so compelling is the sheer scale. Comets aren't rare, they're legion, each one a potential factory for organic molecules. As they loop through the solar system, cosmic rays pepper their surfaces, turning pristine ices into organic, rich crusts. Then, when a comet nears the Sun, heat vaporizes these irradiated layers, releasing their chemical cargo into space or onto any nearby planets. Early Earth, bombarded by comets during the heavy bombardment period 4 billion years ago, could have been showered with these pre-made building blocks. But the Rosetta findings go even deeper. The spacecraft didn't just find glycine, it detected phosphorus, a key element in DNA and cell membranes locked in the same irradiated ices. This suggests comets didn't deliver isolated ingredients but whole molecular toolkits, complete with the rare elements life needs to function. Critics point out that cosmic rays can also destroy molecules, not just create them. Yet the data reveals an elegant balance. While surface layers get battered, deeper ice acts as a shield, preserving delicate organics until they're ready to be released. It's a cosmic game of hide and seek, where radiation both builds and breaks, but over time, construction wins out. The implications stretch far beyond our solar system. Exochum, its icy bodies orbiting other stars, could be undergoing the same chemistry right now, seeding distant planets with glycine and phosphorus. If that's true, then the story of life's origins might not be unique to Earth at all, but a common chapter in the universe's playbook, written one irradiated ice grain at a time. Amid all the theories about life's origins, one question keeps resurfacing: how did the first cells keep their precious chemistry from scattering into the void? The answer might lie not in genes or proteins, but in something far simpler: tiny droplets of fat. Welcome to the Lipid World hypothesis, where the unassuming behavior of fatty acids, the same molecules that make up oils and cell membranes today, could have set the stage for life by creating nature's first microscopic containers. Picture a shallow pool on early Earth, its surface shimmering with a rainbow sheen of oily molecules. These lipids, likely delivered by meteorites or forged in hydrothermal vents, have a unique property. When jostled by waves or heated by sunlight, they spontaneously curl into tiny bubbles called vesicles. Unlike the rigid walls of modern cells, these primitive membranes would have been messy and leaky, but they didn't need to be perfect, just good enough to corral organic molecules into concentrated pockets where chemistry could thrive. Experiments show just how effortlessly this process unfolds. When researchers mix simple fatty acids like oleic acid with water and energy sources, say a splash of salt or a blast of UV light, the molecules self-assemble into hollow spheres within minutes. Even more astonishing, these vesicles can grow, split, and even compete with one another. Some absorb lipids faster, swelling until they fracture into daughter bubbles. Others, laden with stabilizing molecules like phosphates, outlast their neighbors. It's a rudimentary form of selection, unfolding without a single strand of RNA or DNA in sight. But the lipid world isn't just about containment. These fatty barriers could have actively shaped early chemistry. Modern cell membranes are studded with proteins that control what enters and exits, but lipid membranes alone have surprising selectivity. Certain molecules slip through easily, while others get trapped inside, creating microenvironments where reactions that would fizzle out in open water can run to completion. Some vesicles might have concentrated amino acids, allowing them to link into peptides. Others could have trapped iron-sulfur minerals, creating tiny reactors reminiscent of deep-sea vents. Critics argue that without genetic material, these bubbles would hit an evolutionary dead end. Yet here's where the theory takes a fascinating turn. Recent studies reveal that some lipids can fold into shapes that catalyze reactions, much like enzymes. Others carry slight electrical charges, aligning molecules in ways that might have guided the formation of RNA's first strands. It's as if the lipid world didn't just precede the RNA world, it might have laid the groundwork for it. And the evidence isn't confined to labs. The Murchison meteorite, famous for its amino acids, also contains fatty acids capable of forming vesicles. Even Mars's ancient lakebeds show traces of long-chain lipids, hinting that this process could have unfolded on other worlds. So next time you see oil swirling on water, consider this. The same physics that creates those iridescent patterns might have once drawn the universe's first borders, tiny, trembling spheres where chemistry could finally whisper the word life. And if that's true, then the story of our origins isn't just written in genes or proteins, but in the quiet, persistent dance of molecules that decided against all odds to build a wall. The rumble of distant thunder might seem like an unlikely muse for science, but when it comes to unlocking the secrets of life's origins, lightning has always been a star player. While the Miller-Urey experiment made headlines with its sparks and amino acids, another electrifying chapter in prebiotic chemistry often goes untold, one where methane, not ammonia, takes center stage. Imagine a version of early Earth where the air wasn't just thick with water vapor and nitrogen, but brimming with methane, a gas that turns ordinary electric discharges into molecular powerhouses. In a series of lesser-known experiments inspired by Nikola Tesla's work with high-voltage electricity, scientists recreated these methane-rich atmospheres, zapping them with artificial lightning. The results were staggering. Beyond the expected amino acids, the sparks generated a carnival of organic molecules, ethylene, acetylene, even aromatic compounds like benzene, each one a potential stepping stone toward greater complexity. Unlike Miller's classic setup, which relied on ammonia and hydrogen, these methane-driven reactions produced longer carbon chains, the kind that could form the backbone of lipids or the rings of nucleobases. It's as if the lightning wasn't just a spark, but a molecular sculptor carving intricate structures from the simplest gases. What makes these findings so compelling is their versatility. Methane is abundant not just on early Earth, but across the cosmos in the atmospheres of Titan, the plumes of Enceladus, even the icy plains of Pluto. When researchers simulated these extraterrestrial environments with Tesla-like discharges, the same organic menagerie emerged. On Titan, where methane rain falls and electric storms crackle through orange haze, lab experiments show that these sparks could be weaving tholins, the same complex organics detected by the Cassini mission. Suddenly, a gas dismissed as chemically inert becomes a universal artist, painting with the same palette from planet to moon. Yet the story doesn't end with methane's creativity. These electric discharges also solve a puzzle that stumped earlier theories: energy balance. While UV radiation or hydrothermal heat can drive reactions, they often lack the kick needed to forge tougher bonds. Lightning delivers that energy in concentrated bursts, like a blacksmith's hammer striking while the iron is hot. In methane's case, the violent jolt splits carbon-hydrogen bonds with surgical precision, leaving behind reactive fragments eager to link up into something new. Critics point out that methane-heavy atmospheres might have been rare on early Earth, but here's the twist: you don't need a planet-wide blanket of the gas. Even localized methane pockets, say, over volcanic fields or methane seeps, could have hosted these reactions. And the diversity of products suggests that life's toolkit might have been assembled piecemeal, with different environments contributing different molecules. A lightning storm here, a hydrothermal vent there, and soon the pieces start to fit. So the next time you see a storm light up the sky, consider this: those jagged bolts might be more than nature's fireworks. They could be echoes of a time when electricity didn't just power life's rise, it helped design the very molecules that made it possible. And if that's true, then the search for life's origins isn't just about looking for the right ingredients, but listening for the sparks that taught them how to dance. Bubbling up through the fractured layers of Earth's crust, heated fluids could have been the universe's earliest chemists, filtering, sorting, and assembling life's ingredients with quiet precision. Picture a labyrinth of porous volcanic rock, its honeycomb structure riddled with microscopic channels where steaming water laced with minerals circulates endlessly. As these fluids surge through the maze, something remarkable happens. Simple molecules get trapped, concentrated, and rearranged by the rock's charged surfaces, like ingredients sifted through nature's finest sieve. This is the geothermal porous rock hypothesis, where the very geology beneath our feet might have acted as a molecular workshop, turning chaos into order one pore at a time. Yellowstone's otherworldly springs offer a glimpse into how this process could have worked. In places like Mammoth Hot Springs, alkaline water rich in dissolved carbon dioxide percolates through limestone, depositing terraces of travertine as it cools. But beyond the stunning visuals, scientists have discovered something even more intriguing. These waters carry tiny particles of silica and metal sulfides, remnants of the reactions happening deep underground. Lab experiments mimicking these conditions show that when heated fluids pass through mineral matrices, they don't just deposit rock, they can also assemble organic molecules. The porous structure acts like a catalytic filter, trapping carbon compounds while allowing the water to flow, creating pockets where reactions repeat until complexity emerges. The magic lies in the rocks themselves. Minerals like basalt or pumice aren't just passive containers, their surfaces are studded with charged sites that attract and stabilize fragile molecules. Imagine a carbon monoxide molecule drifting into one of these microscopic crevices. The mineral's iron-rich surface grabs onto it, holding it steady long enough for hydrogen atoms to latch on, transforming it into formaldehyde or methanol. Over time, these products get pushed deeper into the matrix, where hotter zones forge them into even more complex structures. It's a conveyor belt of chemistry, powered by Earth's inner heat and guided by the rock's atomic architecture. But here's where the theory gets even more compelling. Unlike tidal pools or lightning strikes, which depend on fleeting conditions, geothermal systems can sustain these reactions for millennia. A single volcanic province might host countless tiny reactors, each operating at slightly different temperatures and pressures, producing a diverse array of organics. Some pores might favor amino acids, while others churn out lipids or sugars, essentially creating a scaled-up version of modern high-throughput chemistry labs. And the implications stretch far beyond Earth. Mars's ancient volcanic plains, like those around Olympus Mons, show signs of similar hydrothermal activity. Even Saturn's icy moon Enceladus, with its subsurface ocean and silica-rich plumes, could be hiding porous rock networks where this silent chemistry unfolds today. If that's true, then the path to life might not always need dramatic catalysts like lightning or cosmic rays. Sometimes all it takes is the steady heartbeat of a planet's warmth, the patience of stone, and the slow, invisible work of water weaving through the cracks. The hazy orange skies of Saturn's moon Titan hide a bizarre secret, a world painted in reddish-brown sludge, where organic goo coats icy dunes and floats in methane lakes. This sticky substance, known as tholin, isn't just alien graffiti. It's the product of cosmic chemistry in action, a process that might have once played out right here on Earth. When ultraviolet light and cosmic rays slam into simple molecules like methane and nitrogen, they trigger a cascade of reactions that churn out complex organic gunk. And while Titan's frigid -180°C surface seems worlds apart from early Earth, the same chemistry could have been brewing in our own planet's primordial skies. Picture Earth 4 billion years ago, its atmosphere thick with methane and nitrogen, bathed in relentless UV radiation from a younger, fiercer sun. High above the surface, photons tear these simple gases apart, creating reactive fragments that link into ever larger molecules. These compounds, tholins, would have clumped into aerosols, drifting downward like microscopic snowflakes, eventually landing in oceans or tidal pools. Lab experiments recreating these conditions produce eerie parallels to Titan's chemistry. When scientists zap methane-nitrogen mixtures with UV light or electrical discharges, The result is a tarry residue packed with amino acids, nucleotide bases, and even the precursors to cell membranes. It's as if the atmosphere itself was a slow-drip coffee maker, steadily brewing life's ingredients. But here's where Titan's alien landscape offers a crucial clue. The Cassini mission discovered that tholins don't just form in Titan's skies, they're also modified by the Moon's geology. When these organics mix with liquid methane or interact with water ice beneath the surface, they can undergo further reactions, creating even more complex molecules. Early Earth's tholins might have followed a similar path, with volcanic heat or hydrothermal activity acting as a second-stage refinery. Recent studies show that when lab-made tholins are simmered in water mimicking ancient seas, they break down into biologically relevant compounds like urea and carboxylic acids, molecules that could have fueled the next steps toward life. Yet tholin chemistry isn't just about what it creates, it's about how those products interact. Unlike isolated molecules floating in a primordial soup, tholins are messy, heterogeneous blends. Some components might stabilize others, preventing destructive reactions. Some could act as rudimentary catalysts, speeding up the assembly of polymers. And because tholins are sticky, they'd naturally clump together, creating microenvironments where concentrated chemistry could thrive. Imagine a tide pool not just sprinkled with organics, but coated in them like a varnish of potential. The implications stretch far beyond our solar system. Exoplanets with hazy, Titan-like atmospheres, worlds like Kepler 7b or GJ 1214b, might be cooking up tholins right now. And if Earth's journey is any guide, those organic hazes could be the first step toward something far more intricate. So while Titan's sludge may seem like an alien oddity, it's really a mirror, one that reflects a time when our own planet was just as strange and just as ripe with chemical possibility. At the bottom of the ocean, where hydrothermal vents spew superheated fluids into the Inkai darkness, an unconventional solvent might have played a starring role in life's molecular origins, carbon dioxide pushed beyond its usual limits. When CO2 is subjected to the intense pressures found near these vents, something remarkable happens. It enters a supercritical state, behaving neither as a gas nor a liquid, but as something in between. This strange form of matter could have been the universe's first molecular matchmaker, coaxing simple organics into bonds that would eventually lead to life. Supercritical CO2 is a shape-shifter of solvents. Unlike water, which polarizes molecules and drives certain reactions, supercritical CO2 operates with a subtler touch. Its molecules slip into the spaces between organic compounds, lowering the energy needed for them to react while leaving no corrosive residue. In lab experiments mimicking vent conditions, researchers have watched as this pressurized CO2 transforms formic acid, a simple molecule common in space and hydrothermal systems, into methylformate, an ester that could serve as a stepping stone to more complex biochemistry. What's striking is how selectively this happens. The CO2 doesn't just randomize reactions, but seems to favor forming stable, energy-rich bonds, almost as if it's curating the chaos. The implications for early Earth are profound. Vents like Lost City, with their alkaline fluids percolating through mineral towers, would have created countless microenvironments where supercritical CO2 could form. As this fluid mingled with hydrogen-rich vent emissions and dissolved metals like nickel or iron, it might have acted as both solvent and catalyst, stitching together molecules that would otherwise ignore each other. Modern chemists exploit this property industrially to synthesize pharmaceuticals without toxic byproducts, suggesting nature could have used the same trick billions of years earlier. But the real genius of supercritical CO2 lies in its duality. In the same environment, it can switch roles, dissolving organics in one zone, then releasing them unchanged when pressure drops, like a molecular shuttle service. This could have solved a key problem for life's origins: how to concentrate fragile products away from destructive heat. Imagine a vent's fluctuating flow creating pulses of CO2 that gather molecules in safe pockets, then deposit them in cooler mineral crevices to accumulate. Critics point out that supercritical CO2 window of usefulness is narrow. It requires precise pressures and temperatures, yet hydrothermal systems are nothing if not dynamic, with countless micro-niches where conditions align. And the evidence isn't just theoretical. In 2019, scientists analyzing ancient vent deposits found ester-like compounds embedded in mineral layers, hinting that this chemistry wasn't just possible, it left traces. Beyond Earth, the potential is even more tantalizing. Jupiter's moon Europa, with its suspected subsurface vents, or Saturn's Enceladus, where CO2-rich plumes erupt into space, could be running similar reactions right now. The universe, it seems, might favor this unassuming solvent, a quiet architect turning cosmic ingredients into something far greater, one pressurized molecule at a time. Sunlight does more than warm the skin. It twists, bends, and shapes molecules in ways we're only beginning to understand. One of life's most puzzling quirks is its stubborn preference for left-handed amino acids and right-handed sugars, a trait called chirality. Like gloves, these molecules come in mirror image versions, yet biology overwhelmingly chooses just one. Why? The answer might lie in an overlooked property of light itself, polarization. Picture the early Earth under a relentless sun, its rays reflecting off ancient oceans or scattering through dense atmospheric haze. Unlike ordinary light, which vibrates in all directions, polarized light oscillates in a single plane. Think of it as sunlight combed into perfect alignment. When this filtered light strikes chiral molecules, something extraordinary happens. Experiments show that left and right-handed versions absorb polarized ultraviolet light differently, breaking down at slightly different rates. The result, over millennia, one form could have outlasted the other, tilting the odds toward life's universal preference. This isn't just speculation. In studies mimicking Earth's primordial conditions, researchers exposed racemic mixtures, equal parts left and right-handed molecules, to polarized UV light. Gradually, one form dominated, sometimes by margins as high as 20%. The effect is subtle but cumulative, like a slow-motion game of molecular survival where sunlight acts as the referee. But here's the twist: polarization isn't random. On early Earth, it would have been strongest near reflective surfaces like water or certain minerals, creating patchwork chiral zones where local conditions favored specific molecular orientations. A tide pool shimmering under polarized glare might have nurtured left-handed amino acids, while a volcanic glass field could have done the opposite. Over time, as molecules mingled through currents or storms, the most stable forms would have spread, setting the stage for life's one-sided biochemistry. Critics argue that polarization alone might not account for the overwhelming uniformity seen today. Yet when paired with other chiral influences like the weak nuclear forces, slight bias, or the catalytic effects of certain clays, the combined effect could have been decisive. And the implications stretch beyond Earth. Mars's ancient lakes, Europa's icy crust, even exoplanets with hazy atmospheres could harbor polarized light strong enough to skew molecular odds. So while chirality might seem like an abstract detail, it's anything but. Without this accidental favoritism, enzymes might not fit their substrates, DNA couldn't twist into its iconic helix, and life as we know it would falter. The universe, it seems, doesn't play fair, but in that cosmic bias, we might just find the reason we're here at all. Deep beneath Earth's surface, where flowing groundwater meets uranium-rich bedrock, nature may have built its first nuclear reactors, not the steel and concrete structures of today, but spontaneous pockets of atomic energy that could have jump-started life's chemistry. The nuclear geyser model proposes that these natural fission reactors, like the 2-billion-year-old Oklo site in Gabon, Africa, did more than just emit radiation. They created dynamic environments where heat, radioactivity, and mineral-rich steam conspired to forge organic molecules on an epic scale. Imagine a hydrothermal vent but powered by uranium decay rather than magma. When water infiltrates seams of pitchblende or uraninite, it can trigger a slow chain reaction as radioactive isotopes split, releasing both energy and neutron showers. In Oklo, this process ran for hundreds of thousands of years, creating temperatures hot enough to boil groundwater into geysers. But here's the twist: these weren't just ordinary steam vents. They were laced with radiation-induced particles that could rearrange molecules in ways geothermal heat alone never could. Laboratory studies reveal why this combination is so potent. When researchers simulate nuclear geyser conditions by irradiating mixtures of water, carbon dioxide, and nitrogen gases thought to dominate early Earth's atmosphere, the results are astonishing. Gamma rays and neutrons transform these simple ingredients into formaldehyde, hydrogen cyanide, and even amino acids like glycine. Unlike lightning or UV light, which deliver energy in brief bursts, nuclear reactions provide a steady drizzle of radiation, allowing delicate syntheses to proceed without violent interruptions. But the real magic happens in the geyser's cycling. As superheated steam carries these new molecules upward, they encounter cooler mineral surfaces, clays or metal sulfides, that act like catalytic scaffolding. Then, when the geyser's pulse subsides, condensed water washes everything back down into the radiation zone, creating endless loops of synthesis and refinement. It's a natural version of modern laboratory reflux systems, where chemists repeatedly boil and condense reactions to drive them toward complexity. The Oklo site offers tantalizing clues that this isn't just theoretical. Analysis of its ancient rock layers shows not just evidence of fission, but also unusual concentrations of rare earth elements metals that could have catalyzed further organic reactions. Even more compelling, certain uranium minerals contain lattice defects matching those created when organic molecules interact with radioactive surfaces, hinting at long-lost chemistry frozen in stone. Critics argue that Oklo formed relatively late in Earth's history, but similar uranium deposits existed 4 billion years ago, when heavier radioactive isotopes were more abundant. And the implications reach beyond our planet. Mars's Arsia Mons region shows uranium concentrations alongside fossil geyser systems. Could nuclear-powered chemistry have unfolded there too? What makes this theory stand apart is its dual-energy approach. Radiation provides the particle bombardment to break stubborn molecular bonds, while geothermal heat offers the thermal gradients to organize the products. Together, they create environments where life's ingredients don't just form, they accumulate, interact, and evolve. The universe, it seems, might have hidden atomic furnaces in plain sight, turning the very rocks beneath our feet into crucibles for creation. Sulfur dioxide might seem like just another toxic gas spewing from volcanic vents, but this unassuming molecule could have been one of early Earth's unsung heroes, a protective shield and chemical matchmaker rolled into one. Picture the planet's first volcanic landscapes, where eruptions belched plumes of SO2 high into the atmosphere, creating a hazy veil that diffused the sun's lethal ultraviolet rays. Without an ozone layer to block this radiation, fragile organic molecules forming in tidal pools or shallow seas would have faced instant destruction. But sulfur dioxide doesn't just scatter UV light, it actively absorbs it, acting like planetary sunscreen for the delicate chemistry unfolding below. What makes SO2 so special isn't just its defensive role, it's a versatile player in prebiotic reactions too. In the oxygen-free air of early Earth, sulfur dioxide dissolved easily in water, forming sulfurous acid that could lower the pH of surrounding environments. This acidity turns out to be a catalyst's dream. Lab experiments show that under mildly acidic conditions, simple molecules like formaldehyde link up more readily into sugars, while hydrogen cyanide, a key precursor to nucleobases, becomes more stable. Even more striking, when researchers simulate ancient volcanic ponds laced with SO2, they observed the formation of thiols, sulfur-containing compounds that are critical to modern enzyme function. It's as if the gas was quietly setting the stage for both life structure and its metabolic machinery. Modern volcanic systems offer a glimpse of this process in action. Near Indonesia's Kawah Ijen volcano, where sulfur vents stain the landscape yellow, scientists have discovered microbes thriving in hyperacidic lakes saturated with SO2. These extremophiles don't just tolerate the harsh conditions, they exploit sulfur's chemistry to power their metabolism, hinting at how ancient life might have co-opted the same reactions. Meanwhile, in the lab, experiments with sulfur dioxide and UV light have yielded even more surprises. The gas can help stitch together carbon monoxide and hydrogen sulfide into thioesters, energy-rich molecules that could have fueled early metabolic cycles without the need for complex proteins. Yet sulfur's most elegant trick might be its ability to toggle between roles. In the atmosphere, it shields. In water, it acidifies. And when irradiated, it becomes a reactive powerhouse. Some models suggest that SO2-rich volcanic plumes could have even generated localized chemical hubs, where periodic eruptions refresh the gas supply, creating pulses of protected, high-energy environments perfect for organic synthesis. The implications stretch beyond Earth. Venus's thick SO2 clouds, though hostile today, might have once offered similar protection during the planet's hypothetical wetter past. Even icy moons like Europa, with their suspected subsurface volcanism, could harbor sulfur-driven chemistry in hidden oceans. So while sulfur dioxide might lack the glamour of cosmic rays or hydrothermal vents, its dual talents, as both guardian and catalyst, make it a compelling candidate for one of life's earliest collaborators. And in that partnership, we might find echoes of a time when the very air, thick with volcanic fumes, wasn't just a barrier to life, but a bridge. For decades, the Unravel World hypothesis has dominated origins of life research, painting a picture where self-replicating RNA molecules kickstarted biology alone. But what if life's first act wasn't a solo performance, but a duet? The peptide-nucleotide coevolution theory rewrites this script, suggesting that proteins and genetic molecules evolved in tandem, each propping the other up like dance partners finding their rhythm. The idea crystallized when scientists noticed something peculiar about modern biology. RNA enzymes called ribozymes often rely on protein helpers to function efficiently, while proteins, in turn, require RNA to build them. This chicken and egg paradox hints at a deeper partnership stretching back to life's dawn. Experiments now reveal how this collaboration might have begun. When researchers mix simple amino acids with nucleotide precursors under mild hydrothermal conditions, the two don't ignore each other, they actively collaborate. Peptides stabilize fragile RNA strands against degradation, while certain RNA structures catalyze peptide bond formation, creating a positive feedback loop. It's as if chemistry itself was wired to encourage teamwork. One striking example comes from lab-created protoenzymes. Short peptides rich with amino acids like histidine accelerate phosphate transfer in nucleotides, the same reaction needed to link RNA building blocks. Meanwhile, RNA strands with loose, floppy sections can fold around metal ions to create pockets that stitch amino acids together. These rudimentary partnerships aren't as refined as modern ribosomes, but they prove a profound point. Complexity doesn't always demand perfection from the start. Even messy, partial cooperation could have given early molecules an edge over loners in the primordial soup. But the theory's real strength lies in solving RNA world's Achilles heel: stability. RNA is notoriously fragile. Its bonds snap under UV light, heat, or even slight pH shifts. Peptides, with their sturdy backbones, could have acted as molecular bodyguards, shielding RNA in mineral crevices or lipid membranes. At the University of Tokyo, scientists demonstrated this by showing how clay-bound peptides extend the lifespan of adjacent RNA strands by 100-fold. Suddenly, the leap from chemistry to biology seems less like a miraculous accident and more like an inevitable alliance. Critics argue that coevolution requires pre-existing complexity. How could two systems emerge simultaneously? Yet nature offers clues. Volcanic glass pitted with microscopic pores might have served as a staging ground. In these tiny chambers, amino acids and nucleotides could have concentrated separately, then mingled when conditions shifted, allowing partnerships to form by trial and error. Meteorites like Murchison deliver both compound classes pre-made, suggesting the raw materials were never in short supply. The implications ripple beyond Earth. If coevolution is life's default pathway, then exoplanets with active geology and diverse chemistry might routinely cross this threshold. No need to wait for a single molecule to figure it all out. Adjust the right environment where peptides and nucleotides can stumble into collaboration. And in that imperfection lies the theory's beauty. Life might not demand a master architect, just a chemical stage crowded enough for partnerships to emerge. So while RNA could have been the first genetic material, it may never have walked alone. The true breakthrough might have been the moment molecules realized they were stronger together. Every second, Earth is bombarded by thousands of microscopic cosmic dust particles, tiny remnants of asteroids, comets, and even distant supernova. Most burn up silently in our atmosphere, leaving nothing but fleeting streaks of light. But what if these minuscule travelers were doing more than just disintegrating? What if, during their fiery descent, they became nature's smallest chemistry labs, forging life's building blocks in the searing heat of re-entry? This theory hinges on a simple but electrifying idea. As dust particles plunge through the atmosphere at hypersonic speeds, they don't just melt, they transform. Friction heats their surfaces to thousands of degrees, while the shock of collision ionizes the surrounding air, creating a temporary plasma sheath. Inside this blistering inferno, the dust's mineral content metals like iron or nickel, or even carbon-rich compounds, could catalyze reactions between atmospheric gases. Imagine a speck of interstellar dust no wider than a human hair, carrying traces of formaldehyde or ammonia. As it barrels downward, the extreme conditions might rearrange these molecules into amino acids or sugars, all within milliseconds. Lab experiments back this up. When researchers simulate atmospheric entry using plasma chambers and powdered meteorites, they observe the formation of complex organics like glycolaldehyde, a simple sugar. The process mirrors industrial plasma chemistry, where raw gases are zapped into valuable compounds, except here, nature provides the energy for free. Even more compelling, spacecraft like Stardust have captured cosmic dust particles with intact organic material, proving these grains can survive interstellar journeys. If they retained chemistry across light years, why not during a brief atmospheric dive? But the magic isn't just in the heat, it's in the aftermath. As the particles slow and cool, their molten surfaces could condense into nanoscale droplets, encapsulating newly formed molecules like microscopic test tubes. These cooled remnants would then scatter across the planet, raining organic cargo into oceans or lakes. Modern studies of seafloor sediments reveal layers rich in extraterrestrial dust, suggesting this delivery system operated for eons. Critics argue that the sheer violence of re-entry would obliterate most organics. Yet recent high-speed camera footage of meteors reveals something unexpected. While the outer layers vaporize, the cores often remain intact, shielded by their own ablative heat shields. It's a cosmic twist on survival. The same physics that lets astronauts return safely might have protected delicate molecules 4 billion years ago. The implications stretch beyond Earth. Mars's thinner atmosphere would have allowed more dust to reach the surface with minimal heating, potentially sprinkling raw materials directly onto its ancient river deltas. Even Venus's hellish skies, where metallic particles form mysterious high-altitude layers, might host similar chemistry today. So the next time you see a shooting star, consider this. that fleeting spark could be more than just space debris burning up. It might be the universe's way of running an experiment, one that, over countless trials, helped turn stardust into the chemistry of life. And if that's true, then life's origins might not rely on rare, perfect environments, but on the relentless, invisible rain of cosmic grit, each grain a potential matchstick striking against the atmosphere's vast tinderbox. At the coldest edges of the universe, where temperatures plunge hundreds of degrees below freezing, chemistry should grind to a halt. Bonds freeze in place, reactions slow to a crawl, and molecules become locked in icy prisons. Yet life's building blocks somehow emerged even in these frigid wastelands, and the answer might lie in one of quantum physics' strangest phenomena, tunneling. Picture a hydrogen atom trapped in an ice grain deep within a molecular cloud. Classically, it lacks the energy to break free or react with neighboring atoms. But in the quantum realm, particles don't play by ordinary rules. There's a tiny but real chance the atom will vanish from one side of an energy barrier and reappear on the other, as if teleporting through solid ice. This ghostly trick, called quantum tunneling, could have allowed reactions that defied the cold, stitching together molecules that should have remained inert. Experiments in ultra-cold chemistry labs reveal just how powerful this effect can be. When scientists chilled mixtures of hydrogen and carbon monoxide to near absolute zero, reactions still occurred millions of times faster than classical physics predicted. The culprit, tunneling, let hydrogen atoms bypass energy barriers, forging formaldehyde even in conditions that should have frozen all chemistry. Even more astonishing, tunneling isn't random. Certain ice structures, like the crystalline lattices found in interstellar grains, seem to guide these quantum jumps like microscopic racetracks, steering atoms toward specific reactions. The implications ripple outward. Ice-coated dust pervades the cosmos, from comet nuclei to the rings of Saturn, and tunneling could have transformed these icy flecks into factories for prebiotic molecules. Recent observations of distant nebulae support this. Telescopes have detected complex organics like methanol in regions so cold that conventional chemistry should be impossible. Quantum mechanics, it seems, handed the universe a cheat code, enabling reactions where none should exist. But here's the twist: tunneling might do more than just bypass the cold. Some theorists suggest it could explain life's chiral bias too. In certain asymmetric ice structures, quantum effects favor one molecular handedness over the other, potentially tipping the scales toward the left-handed amino acids life eventually adopted. It's a dizzying thought that the quantum quirks of tiny ice grains might have set the stage for biology's uniformity billions of years later. As for what this means beyond Earth, ice-heavy worlds like Europa or Pluto's moon Charon could be tunneling hotspots even now, their frozen crusts humming with quantum-fueled chemistry. And if that's true, then the story of life's origins isn't just written in stardust or lightning, it's etched into the very fabric of reality, where particles wink in and out of existence, stitching together the improbable reactions that made our existence possible. The universe, it seems, never needed warmth to cook up life, just the strange, silent magic of quantum uncertainty, turning ice into an alchemist's workshop, one tunneling atom at a time. After this whirlwind journey through 30 fascinating theories, from radioactive beaches to quantum tunneling in interstellar ice, one thing becomes strikingly clear: the universe is far more creative than we ever imagined. The origins of life's first organic molecules might not hinge on a single eureka moment, but on a symphony of processes, each playing its part across time and space. Perhaps hydrothermal vents forged the foundations while comets delivered the finishing touches. Maybe tidal pools concentrated the ingredients and cosmic rays stitched them together. Or could it be that all these environments, in their own chaotic yet precise ways, contributed pieces to a puzzle we're still assembling? The beauty of this mystery is that it refuses to fit neatly into one box. Some theories feel almost poetic, like the idea that life's building blocks were crafted in the silent darkness of deep crustal chambers, or that the faint glow of radioactive minerals guided chemistry toward complexity. Others, like volcanic lightning or nuclear geysers, remind us of nature's raw power to turn destruction into creation. And then there are the wild cards: quantum tunneling in ice, or sulfur dioxide's dual role as both shield and catalyst, proving that the universe operates on rules we're only beginning to decode. So where does that leave us? Instead of searching for a lone winner among these theories, maybe the real answer lies in their intersections. Life is resilient, adaptable, and opportunistic. Why wouldn't its origins be the same? The molecules that became us might have taken detours through comets, endured cosmic radiation, simmered in hydrothermal vents, and even hitchhiked on interstellar dust before finding their way into Earth's primordial soup. Now it's your turn. Which of these ideas sparks your curiosity the most? Do you envision life's beginnings in the violent energy of lightning or the patient chemistry of clay minerals? Could the answer lie in the cold vastness of space or the hidden depths of our own planet? Drop your thoughts in the comments, because the story of how we got here isn't just for scientists to unravel. It's a conversation for all of us as we piece together the greatest detective story of all time, the cosmic origins of life